In our last video, we talked about how we can use the ideas and concepts about difference equations and diagonalization in order to figure out a closed formula for the nth Fibonacci number. In this video, we're actually going to use the same concept. However, we're going to tackle a very different problem, and it's about a steady state of population. That is, about the distribution of population in a closed system. Alright, so let's look at this problem. And by the way, this process we're going to tackle today is called the Markov process. Each year, 10% of the people outside of California move in, and 20% of the people inside California move out. We're also given that we start with Y0 people outside and Z0 people inside. So, what does this mean? Well, this means we have a closed system. Nobody is moving outside of the system, and nobody is moving inside to the system. However, we do have two areas. We have in California and out California. Inside California, we have people moving out, immigrating. And outside of California, we also have people moving in, immigrating. Now, how can we represent this using a matrix system of equations? That's the most primitive method of deriving a matrix. What we have here is y1. Well, using this conversion, we have y1 is equal to the people outside of California after 1 year. So this is 0.9 y0 because 10% of the people outside of California moved in, and we have 0.2 people in California moving outside. So we have to plus 0.2 z0. And similarly, we can use the same expression to say that this is equal to 0.1 y0 and 0.8 z0. Now notice that the columns over here add up to 1. Okay, so putting this into a matrix, what we have here is we have a vector that's equal to a matrix and then we multiply by the, let's say, the initial vector. So that's y0, z0. And we have a difference equation. Notice that this is u1, and this is a, this is u0. Of course, we're going to use this expression over here. And for this problem, our interest is to compute, is there a converging population distribution in an infinite amount of time? So we want to see what u of infinity is. So what u of k is when k approaches infinity. Fantastic. So that is our goal. First of all, we're going to look at a. We're going to diagonalize a. How do we do that, though? To diagonalize a, what we'll do is we'll find out the eigenvalues of a. So, computing this, we directly have this thing, 0.9 lambda, 0.2, 1, and 0.8. And we're going to put that in the determinant. That is equal to 0. Now, computing this, I'm not going to go through the full detail, but we get lambda squared minus 1.7 lambda plus 0.7. That is equal to, well, lambda minus 1 times lambda minus 0.7. We basically factorized it into two binomials, and that is equal to 0. Now, using common GCSE math, we know that for a quadratic, we only have two roots, and these are the two roots, right? So, lambda 1, our first eigenvalue, is equal to 1, and lambda 2 is correspondingly 0.7. Now, its eigenvectors can be put in an eigenvector matrix. I encourage you to do this on your own, but I'm going to diagonalize this very, very quickly. So, what we basically do is we put eigenvectors into S, we compute the inverse of S, and we put eigenvalues into the diagonals of an eigenvalue matrix denoted by big lambda. Therefore, A is equal to S lambda S inverse. Well, this is equal to, I'm simply going to write what we have when I compute all of this over here. We have this times our eigenvalue matrix. And last but not least, we times it by our inverse of the eigenvector matrix. This is what we get. Fantastic. This looks pretty auspicious, but what we need over here from our difference equation is a to the k. But that's okay, because we know that when we raise a to the kth power, we are raising lambda to the kth power, which raises all the diagonal terms to the kth power. Now, 1 to the k is always 1, so we can directly omit k as the exponent. Now we can substitute our a to the k into our difference equation. So u of k, which is equal to a to the k u naught, is equal to s lambda to the k S inverse times u naught. Well, that's pretty easy. We can basically copy this out front. And then we can multiply our u naught, which is y naught z naught. Okay, that's what we have. Now, what we're considering is when k approaches infinity. But let's first expand the matrices, that is to multiply the matrices together. Well, computing this, we keep the first matrix. We write the second matrix as follows. And we multiply the third and the fourth matrix, giving us y naught plus z naught. And y naught minus 2z naught. Well, multiplying this further, we keep our first matrix again because we're not over here yet. And then we times this by our eigenvalue matrix times this matrix. So we have this. Fantastic. Now notice that this expression is times by 1 from this. But because anything times by 1 is itself, we omit the 1. Alright, so next of all, let's multiply these together, which gives us y naught z naught, 2 over 3, 1 over 3, and then we add this expression. Fantastic. Now we have a much more beautiful equation to consider. When k approaches infinity, notice that this term, this whole term, this part, these all converge to 0 because 0.7 to the k converges to 0 when k approaches infinity. And 0 times anything is basically 0. Of course, this is a constant, so we don't have to worry about, for example, asymptotic analysis or how a function is growing faster than another function. So that's it. So these converge to 0, which gives us finally, as k approaches infinity, we have y naught plus z naught and this vector. Fantastic. Now, this is equal to u infinity because k is approaching infinity. And notice, these are all constants, which means our population actually converges to a final distribution. And this is really interesting because notice, our population distribution only depends on the sum of the population inside of California and outside of California. What does that mean? Well, that means if y0 is equal to, for example, 1,500 and z0 is equal to 1,500, well, the total population, which is their sum, is equal to 3,000, which yields a population of 2,000 and 1,000. But if the population y0 is 0 and z0 is 3,000, well, their sum is again 3,000. And so the population actually also converges to a distribution of 2,000 and 1,000. So as long as the total population is the same, we don't have to worry about what value y0 and z0 are. That's really interesting. And U of k actually converges to a steady state. And that steady state is the eigenvector associated with the eigenvalue equals to 1. Well, you might ask, of course, we know this is the eigenvector, but it's multiplied by a scalar, so how is it still the same eigenvector? Well, notice, eigenvectors, when multiplied by a scalar multiple, are always still an eigenvector. So if we have an eigenvector x0, then cx0 is still an eigenvector. Alright, and this concept of state stability also leads us to concepts about neutral stable, stable, and unstable. So how probabilities are unstable, how population growth are unstable, and how matrices in general are just unstable. And there's actually applications in economics too, like the Leontief's input-output matrix, or the prizes in a closed input-output model, Leontief matrix, von Neumann's model of an expanding economy, although I don't really know much about it. But these are all really interesting concepts. And that's it. Thank you for listening, and in my next video, I probably do something about calculus. It's very much different from linear algebra, but the way we think is basically very similar. It's about rigor and how we use induction to prove other things. Thank you for listening, and see you in the next video.